We'll take just a second. All right, everyone, we're live. It's my pleasure today to give you Liang Fu from MIT, who's going to be talking not about topology today, apparently, but novel pairing mechanisms involving a third electron. As usual, please feel free to unmute yourself and ask questions if you have any. And otherwise, we will have a question session at the end of the talk. Please, Liang, go ahead.
Okay, yeah, thank you, Adrian, for inviting me, and it's a real great pleasure. So yeah, good afternoon, everyone. I'm going to talk about today about some new pairing mechanism for superconductivity, come from repulsive interaction, electron-electron repulsion itself, without relying on the phonons. And so let me start by thanking my collaborators. So this work will not be possible without working with them, and it started right before the pandemic in collaboration with Kevin Slagle. And since then, our thinking has been further developed and generalized into some related but new directions. And the two recent works were done in collaboration with my student Val Kreppel at MIT. So let me first start by reminding you the essential ingredients of the BCS theory for superconductivity in conventional metals. And here, as we all know, that the electron attraction comes from the interaction with the phonons. And the electron-phonon-induced interaction is always weak compared to the direct Coulomb repulsion between electrons themselves. However, superconductivity becomes possible due to a crucial property, the so-called retardation effect. So basically, when two electrons repel each other, they move apart, and that reduces the Coulomb interaction strength. On the other hand, the lattice vibration has a much slower dynamics, and therefore two electrons can still interact through the lattice relaxation, through the lattice vibration, without being close to each other at the same time. So the net effect of this retardation is that the effective Coulomb repulsion is renormalized and greatly reduced from the mu to the so-called mu star. So then the net interaction strength is given by the electron-phonon induced attraction lambda minus mu star, and this can be attractive. So this phonon mechanism again relies crucially on the retardation effect, and this further relies on the fact that the electronic energy scale, the Fermi energy, far exceeds the phonon energy scale, which is the Debye frequency. And this condition is satisfied in simple metals, and this is the justification of the BCS theory. Now, on the other hand, we also know that there are many unconventional superconductors appearing in systems with strong interaction and with narrow electronic bands. So these include the cuprates, the original high temperature superconductors, the heavy fermion systems, and more recently, as we all know, the magic angle graphene, where the bandwidth is only on the order of a few tenths of millielectron volt. So in this case, there is widely believed that the superconductivity arises from the electron repulsion itself, that is far dominates over the phonon energy scale. So this motivates us then to look for the electronic pairing mechanisms, where the attractive interaction comes from the Coulomb repulsion itself without relying on phonons. And again, this is a subject with a long history and still very active research. And here I list a few such mechanisms, starting from the Kohn-Luttinger mechanism, this, as we will see, that this mechanism is a very a classic example, and it's well established in the limit of a weak interaction strength. And then these are some other examples. For example, if the system is close to some kind of a magnetic instability, then the spin fluctuation is enhanced, and this then serves as some kind of a bosonic pairing glue, which can some collective spin modes can replace the role of phonons in mediating the attractive interaction. And finally, there are very exotic ideas, such as doping a quantum spin liquid or a mod insulator. The idea there is that maybe there is some sense in which one can think of an insulating state as having preformed electron pairs, and somehow doping then liberates these pairs, and they condense into a superconducting state. I think the idea is quite interesting, but it's also very vague. So, so let me spend a few minutes discussing the Cone-Luttinger mechanism first. So here, the attractive interaction comes from the dynamical screening of the Fermi sea itself. So this mechanism works in a repulsive electron system in a normal metal. And so as we know that in the presence of the interaction, in the presence of a Fermi sea, by polarizing the Fermi surface, one can create some kind of attractive interaction in a high angular momentum channel. And this effect is actually, this mechanism is actually controlled. It's asymptotic exact when the interaction strength is weak compared to the Fermi energy. However, the problem then is that in this analytically controlled regime, the superconducting transition temperature Tc is also very small. In fact, the ratio of Tc and the Fermi energy is exponentially small in some dimensionless coupling constants. And this dimensional coupling constant is always much smaller than 1 when the theory is controlled. And therefore, the ratio of Tc and Tf is guaranteed to be a small number. Okay, this is all well understood. And now, when we look at the unconventional superconductors that are experimentally observed, many of them actually have a very strong coupling effects with large ratio of the superconducting Tc and the Fermi temperature. So these are some examples, and these include, for example, the cuprates, the heavy fermion compounds. So the y-axis here are the Tc, the x-axis is the Fermi temperature. So as you can see that many of these compounds belong to a strong coupling regime, including the magic angle graphene. So, and these are some examples. For example, if you look at the transition temperature Tc as a function of the carrier density in magic angle graphene at the filling of 2 holes per Moiré unit cell, we have insulating states. And you see, remarkably, doping this insulating state almost immediately give rise to superconductivity. And the ratio of Tc and the Fermi temperature can reach around 10%. This is significantly higher than this ratio in ordinary metals, right? And here's another example. We will talk more about this later. There's a material known as zirconium nitrogen chloride. It's a layered material that can be exfoliated into thin flakes. And this is recent work from Iwasa's group in Japan, again showing that by ion liquid gating, electron doping in zirconium nitrogen chloride leads to superconductivity. And as you can see, that the ratio of Tc over Tf again can reach to about 10%. Right. So these are anomalously large Tc over Tf compared to weak coupling conventional superconductors. So this motivates us to look for a mechanism for superconductivity from repulsive interaction in the strong coupling regime with a large Tc-Tf ratio. And this is actually a very difficult task when interaction strength is large. Usually, it's hard to find an analytically controlled method. And also, when interaction strength is strong, there may also be other competing states, such as stripes, for example, that has been found in the pure Haber model in the square lattice. And the stripe state seems to win over the superconductivity in some realistic parameter regime relevant for cuprates. So, so with this, let me now move on to the main part of this talk. I'm going to introduce a new mechanism. We call it a three-particle mechanism for pairing. And this idea is actually very simple. It can be understood both in the real space and in K-space. So in real space, as you can see here, if we consider, for example, two electrons marked in red, these are, for example, two doped electrons in the ionic insulator. And we can see that because of the direct repulsion between all these underlying electrons, the motion of electron can become highly correlated. So for example, in order for electron to move from location, this electron to move from here to here, it can first knock out an electron, the third electron, and then replace the hole that's left behind. And this kind of a second order process, the intermediate state would involve three electrons on these marked in red surrounding an empty sites, right? So it turned out that this three particle here, because of this three particle intermediate state, it leads to an effective attraction between electrons 1 and 2. And we will see this more explicitly soon. Alternatively, you can think about this in momentum space, that we start with a insulator where the valence band is all occupied, and then consider two doped electrons in the conduction band. So because of the Coulomb interaction, there can be a virtual process where one electron in the field bands virtually transition into the conduction band and then comes back. So this virtual process, again, we will see that leads to an effective attraction between the two conduction electrons. Okay. So, so this idea is simple. What our main contribution is that we realized that there's actually a way to develop a fully controlled theory for this mechanism based on the kinetic energy expansion. Instead of treating interaction as a small parameter, we deal with our method works in a strongly interacting regime, and we treat the kinetic energy as a small perturbation. Okay. So, this idea and this method works very generally, but to be concrete, let me give an example, okay, that I'm going to focus on in the rest of this talk. And so as an example, we consider, for example, a honeycomb lattice with two sublattices A and B that have different on-site potential. And for simplicity, we first consider the case of spinless fermions or spin-polarized fermions, and later we will generalize it to the spinful case. And these electrons have then nearest neighbor repulsion. Basically, this is just an extended Haber model on the honeycomb lattice with a potential bias V between the two sublattices. So our model is actually motivated by recent experiments on semiconductor morays, such as the twisted homobilayer MOS2. Without going into the details, let me just say that these monolayer MOS2 are large gap semiconductors with a valence band edge around the gamma point. And when you form two layers, we combine the two layers to form a Moray lattice. The band edge is spatially modulated so that the potential minimum, the Moray potential minimum, forms a honeycomb lattice. So, so this provides a solid state system that realizes the multi two-band Haber model on the honeycomb lattice with extended interaction. And yeah, let me skip this. So in this model, we can see that because of the sublattice potential difference, the electrons prefer to be on one sublattice, let's say the blue sublattice. And at the filling of one electron per unit cell, again, here I'm dealing with a spinless case. So in this case, at the filling of a one electron per unit cell, we get an insulating state. Electrons essentially occupy all the blue sites. And this is a very simple ionic insulator. It's connected smoothly to the limit T hopping is 0. It's also smoothly connected to the non-interacting banding insulator when V, the repulsion, is turned off. So this is perhaps the most boring insulating state you can think of, with no topology or anything like that. Okay, so very simple band insulator or ionic insulator. And the conduction and valence bands are separated by a large gap delta. And in the small t limit, the band width, one can work it out, is on the order of t squared over delta plus v. So when v equal to 0, this is just the bandwidth of the non-interacting electrons. And we will see that when v is present, we will derive this from a perturbative expansion in hopping t. So, what's interesting about this kind of boring insulator? The remarkable thing is that when you dope electrons into this insulator, into this large gap insulator, doped electrons immediately attract. Okay, and in particular, let's consider the simplest case of just 2 doped electrons. We will show that they form a bound state in the F wave channel. And this is interesting because, remind you again, this model consists of purely repulsive interactions, right, between nearest neighbors. The bare interaction is repulsive, but 2 doped electrons attract. And one can find the exact expression for the binding energy, again, in a small t limit, and that is shown here. This result is fully non-perturbative in the interaction strength V. Okay, so when V is small, this dimensionless coupling constant that characterizes the pairing interaction is proportional to V squared. However, this result is exact, to all orders in V, and it deviates from V squared at large V. Okay, and here again, the result, that we find an attraction between 2 doped electrons despite the bare repulsion, or you can say because of the bare repulsion V. This occurs without relying on any Fermi surface. We're just dealing with a problem of 2 electrons, 2 doped electrons. It does not rely on any spin fluctuation. We're dealing with the spin polarized, fully spin polarized regime. There's also no RVB physics. There's no competing order. The system at the parent state we start with is just a very simple featureless insulator. Okay, so now building on this result of 2 electrons, well, we can further determine the ground states at finite doping density. And in this case, we will see that the ground state is a BEC, BCS superconductor. And depending on the ratio of the 2 particle bound state and Fermi energy, it can either be the BEC or BCS regime. So as the density increases, it crossovers from BEC to the BCS regime. Okay, so we can get BEC, BCS physics in the electronic system with repulsion. So how are these results obtained? And what is the microscopic origin of the attractive interaction between 2 doped electrons? And let me first, give you a warm-up example that illustrates the essential physics. Instead of considering an extended lattice of a honeycomb lattice, let's just consider a very small part of the honeycomb lattice consisting of 4 sides. A central side, and the B, let's call that A side, surrounded by 3 B sides. The central side has a lower on-side potential, minus delta. So as you start to adding electrons into the system, the first electron occupies the center side, and then the second electron occupies one of the 3 adjacent sides. The third electron occupies yet another adjacent sides. So in the limit, when the hopping T is 0, we can work out the energy of all these different states exactly. And we find that starting from having 1 electron in the system, adding 2 electrons costs energy that is twice the energy of adding 1 electron. Okay, and what this means is that the pair binding energy is exactly 0 in this simple point model in the absence of any kinetic energy T. Now, once we include the kinetic energy T, so this hopping T always between nearest neighbors it always connects states that are far separate in energy, because this energy gap delta is large. The energy difference between the A and B sites is large. So hopping would induce a transition from a low energy state into a high energy state. So therefore, to capture the effect of T requires second order perturbation theory. And we know that in second order perturbation theory, we need to work out the energy of the intermediate states. And here I show here the energy of all the configurations of all the intermediate states. For example, in the case of one electron, the intermediate states corresponds to the central electron hopped into one of the adjacent A sites, and that's shown here, that has an energy delta. Now, when you have consider the two electron system, and in this case, the intermediate states corresponds to the configuration shown here. And in this case, once a central electron hops to an adjacent site, it saves the original repulsive interaction V, okay, that is previously present. So as a result, the energy cost of this transition is delta minus V, right? And likewise, if you think about the 3 electron case, in this intermediate states, when this central electron hops to adjacent sites, it recovers the 2 repulsive energy V, 2 units of the repulsion V, and therefore the intermediate state has energy delta minus 2V. So as we can see that because of this effect, that the virtual states, intermediate states, costs less energy when we have 2 neighboring electrons. Because of this, we find that adding 2 electrons into the system now costs less energy than twice adding 1 electron. Okay, the binding energy now becomes attractive. Okay, so this is the microscopic origin of the attraction. Despite that, we start with a system of pure repulsive interactions, and we can see that this attraction is deeply quantum mechanical of origin. It comes from the kinetic energy T. Okay. So again, for this toy model, to summarize, as we increase the chemical potential, it will change directly from the ground state will change directly from having 1 electron to having 3 electrons, skipping the case of 2 electrons. In other words, this quantum molecule, it shows a valence skipping. It effectively, it's like a negative U center. Okay, it prefers to have charge 1 or charge 3, but not having charge unequal 2. Any question? Okay, so we can again carry out the same calculation for the entire lattice problem, and we're going to again treat the kinetic energy as a perturbation, the hopping as a perturbation. So to first order in T, it inevitably would create a hole on the A sites. It will inevitably transfer electron from A to B sites, and therefore it will cost energy delta, right, which is the energy difference between A and B. So in order to derive the effective model at low energy, then we have to go to at least second order in T. Okay, and again, in this second order perturbation theory, the intermediate state will involve all different kinds of configurations. And for example, starting from a region where you have an A electron virtually hop into adjacent sites, then the intermediate state consists of a dipole. Now, the same process, if in the presence of an adjacent B electron, will then create an intermediate state consisting of a polaron. Or if an A electron make a virtual hop to in the presence of 2 adjacent B electrons, then the intermediate state will consist of a trimer. And these different intermediate states, again, have different energy cost. The trimers cost the least energy. Okay, so for that reason, it is preferable for 2 electrons to be adjacent to each other. That's just like in the toy model that I've shown. The way to systematically derive all of this is to use the so-called Schrieffer-Wolff transformation, and I'm not going into the details, but this is a rigorous method that decouples the low and high energy manifold. It eliminates the off-diagonal terms to first order in T. And after this transformation, we get an effective Hamiltonian that acts in the Hilbert space of doped electrons. And here is the expression. We get the kinetic energy for doped electrons. That is on the order of T squared over delta plus V. So you can check that in the limit V equals 0, this is precisely recovers the non-interacting bandwidth in the large delta limit. And in addition, we find various kinds of interaction terms. There's a nearest neighbor interaction between two doped electrons on the lattice, on the triangle lattice of the B sites. So this V really corresponds to second neighbor interaction on the original honeycomb lattice, right? So one general feature is that once you eliminate some high energy degrees of freedom, you will generate interactions that are previously absent. Okay, so this, and here we show explicitly. So the original model only has nearest neighbor interactions, but once we eliminate all those field electrons, we generate a second neighbor repulsive interaction. And this actually is repulsive when V is small and eventually becomes attractive when V is large. But in addition, there are more interesting terms. In particular, this lambda term is in correlated hopping. We call it correlated hopping. So this corresponds to a hopping process of electron from site I to J, but it's modulated by whether a second electron at adjacent site K is present or not. So it has a form of a density multiplied by a hopping term involving in total 3 sites, hopping from site I to K, controlled by the occupation of site J. So so here, and further, there are also 3-body repulsive interactions. So here, because our method is exact, we can work out all these expressions. So this result, it holds at any doping, and it holds at any interaction strength V. So it's fully rigorous, provided that hopping T is small compared to delta. And also, the Schrieffer-Wolff transformation preserves the Hamiltonian dynamics. So the effective interaction is instantaneous, just like the original Hamiltonian. And so this is, again, what we will see is that the pairing interaction obtained from eliminating very high energy degrees of freedom, it will lead to an attraction that is instantaneous. It's not retarded, unlike the electron phonon case.
Leon, I have a question.
Yes, please.
When you say independent of doping, what if you dope it till the valence band, the conduction band is completely filled?
Yeah, you can work it out. If it's completely filled, this model still works. It's just like now that this you're dealing with the doped electrons, but it's filled, complete filled. Right? So, for example, you can work out the case of the dispersion of one hole in the conduction band, and it will be governed exactly by this Hamiltonian. You can treat the induced Hamiltonian also at the filling of all except one, for example. And we can, and it all works out. Yeah, we did that check.
Okay, thanks.
Yeah. So that's the important point I want to emphasize. Even though the most of my talk is going to deal with low doping limit, but this formalism actually is exact at all dopings to second order in T squared. Yeah, so one can in principle go to high orders, but the calculation become much more messy. Okay, so one more remark that we can also compare the this exact Hamiltonian with the projected interaction. So when when you have an insulator and you dope the insulator slightly, it is tempting to just forget about the field bands and directly project interaction into the conduction band. And this projection method is exact when the interaction strength is weak. When V is much smaller than delta, then the projection method approaches the exact result. But as we can see from here, that as V increases, the projected interaction that's shown by the dashed line and the exact results that takes into account of this interband renormalization, takes into account of this interband excitations, they differ quite a bit, substantially, I would say. They differ really substantially. And we see that the interaction is really strongly normalized, even for V over delta, around like 0.3. And in the limit, when V go to infinity, this effective Hamiltonian, the bandwidth of doped electrons actually vanish, but we are still left with interesting interaction effects. So this is the model is actually very rich. So okay, but so let me now first analyze this problem at a level again of 2 doped electrons. We can solve this lattice Hamiltonian exactly for 2 electrons, and we find an F-wave pairing. The 2 electrons attract, form F-wave bound states, and in the limit V go to infinity, this F-wave pair just resonate within a smallest triangle of the B sites. And here I show the binding energy as a function of V over delta, that's plotted in blue, and also the Cooper pair size shown in red. So as you expect that as the repulsion increases, the bound state size shrinks and the binding energy increases, and it eventually saturates. So we can right. So this all sounds very counterintuitive, right? But we start with a model with full repulsions, but we actually find that 2 doped electrons attract. So I've shown you the rigorous derivation, but if you are unconvinced, at least I can say that we also did the exact derivation for the full model with again work of Val, a student, and here's the pair binding energy for a system as large as 30 sites as a function of V over delta. And as you can see that the binding energy is attractive, so it means that there's pairing going on. And what's plotted here is a pair-pair correlation function. And again, you can see that attraction is present, pairing is present in this repulsive model. So, so now let me move on to the case of low densities. And again, at low density, the doped electrons actually live on the bottom of the conduction band. And in the honeycomb lattice, there are 2 band bottoms at K and minus K. So the system is a 2-valley electron gas. And then one can sort of write the interaction in momentum space and then zooming in into the bottom of the conduction band. This allows us to derive rigorously continuum description. And in this continuum theory, we have 2 flavors that emerge. The flavors corresponds to the 2 valleys, and the leading order, there is an interaction, contact interaction between the 2 flavors. And this contact interaction is attractive. So at low density, the system really becomes essentially pseudo spin 1/2 Fermi gas with attractive contact interaction that is known then to have a BEC-BCS crossover. It's a superconducting state, and it can be tuned from the BEC regime at low doping to the BCS regime at higher doping. And in this description, the paired state looks like in the S-wave channel, but that is exactly correspond to the F-wave pairing in the lattice model, because the 2 flavors, the 2 pseudo spin up and down corresponds to the 2 valleys, and the pairing between the 2 valleys for the spinless case has F-wave symmetry. So if you do a reflection symmetry that interchange the 2 valleys, the Cooper pair wave function would change sign. That exactly means F-wave on the lattice. And one of the so we can actually because we have all the exact expressions for the in effective Hamiltonian, and when we map into the continuum model, we can really work out these continuum model parameters. So I will not show you the details here, but for example, when we look at the binding energy in the continuum theory, it is characterized by a dimensionless coupling constant, and that we can ultimately relate it to the original model parameter V and delta. And there's also a UV cutoff in the continuum theory, and that we fix by requiring a match, by matching the binding energy at the infinite interaction strength limit. And there, we know the exact results from the lattice model. So once we have this, then we can compare the lattice calculation for 2 electrons versus the continuum model theory for 2 electrons with no further, no adjustable parameter. And you can see that they really agree with each other. So, so that's why we're confident that the physics at low doping is entirely, excuse me, described by this continuum theory of spin 1/2 Fermi gas with attractive interaction. And that is the origin of the BC-BCS physics in this repulsive model. So again, now I can borrow some results from the BC-BCS community. It is known, for example, that the superconducting TC can be captured nicely by this formula over a wide range of conditions. It's proportional to the geometric mean of the Fermi energy and to the 2-particle binding energy. And this formula works all the way up to the case of TC is about 10% of the Fermi temperature. And so again, again, translating into our context, it means that we have a dependence of TC on the carrier density, which has a square root of doping dependence. Okay, this is again counterintuitive. In the 2D system, for example, the density state is constant, is independent of doping. So if you take the BCS type of theory, electron photon superconductors, then one naively at least would expect the TC to be independent of doping. Or if you take the Lagrange mechanism, then we know that TC is the energy scale of TC is set by the Fermi energy, which will be then proportional to the density, not to the square root density. Right. So this is one of the interesting predictions, or let's say the features. Excuse me. Features of our theory that the TC is proportional to the square root of doping, and right. So another interesting feature is that the ratio of gap and TC, the BCS theory says it's 1.7, but our theory predicts it's 4.8. Okay, and this is true, not coming from anything like the BEC physics. So at the doping that are not too low, when the Fermi energy is higher than the 2-particle binding energy, even in what cold atom people call the BCS regime, we have to remember that the attraction is instantaneous. It's not cut off by the bifrequency. And for that reason, even in this regime, the delta over TC is already almost 3 times higher than the BCS value. So this is, again, another interesting feature. So one can further, extend this result to finite density, beyond just low doping limit. And there we have to rely on a mean field method. And we find that the F-wave pairing is very robust. It extends to a very wide range of dopings. And the F-wave pairing at low density, it's centered around the Fermi surface is centered around K and K prime point. So that's fully gapped. But above a quarter doping, the Fermi surface from K and K prime merge, and then the nodes developed. So there's a transition from a fully gapped F-wave pairing to a nodal F-wave pairing. We can further, again, support these results by exact dilation calculations of the original model, and we can see that that from the dependence of the ground state energy on the flux, we see that it has an H/4E flux dependence, showing the presence of pairing. And one can also twist the boundary condition and look at the ground state energy dependence, then that reveals the charge stiffness. And we see that both the pairing gap is present and the stiffness is finite in a wide parameter range, supporting our conclusion of superconductivity in this model with repulsion. Okay, any questions? What time is it? How much time do I have, Adrian?
20 more minutes, I think. I mean, in principle, as long as the audience doesn't complain, we can go on forever. But yeah, let's try to stick to the, to within the hour.
And you said we have 10 minutes or
20.
20. Okay, perfect. Yeah, and I see there's a question here. Yes.
Can I ask a question? Can I ask a question?
Yeah, sure.
Okay, Victor Yakovenko. So question is, this F-wave superconduction pairing, does it break time reversal symmetry?
It doesn't. This is on the triangle lattice, right? F wave is a one-dimensional representation.
Ah, okay, okay, it's one-dimensional. Okay, okay, thanks.
Can I ask a question?
Yeah, sure.
Daniel Humsky. You started by reminding us about this collateral mechanism. And in collateral mechanism, indeed, there is always pairing, but in a Cooper pair, it's with large momentum. And TC was always large. That was also studied in detail by Pitaevsky long ago. And the TC was small, not because of the coupling, but rather because of this large relative orbital moment. In your case, you also have F-wave pairing. That's also large orbital moment. So I wanted to better understand what is the relation of your picture with this general quadrilateral thing.
Right. So
Looks
again,
like your thing is kind of a specific realization of the general mechanism, or
so it's very different. Yeah. So yeah, it's an excellent question. So so in the Kohn-Lattinger case, yeah, it relies on the existence of Fermi surface. So another way of saying this is that if you just have two electrons in the system with repulsive interaction, they will not form a bound state. Right. Here, I have two doped electrons only, and they already form a bound state. Right. So this is very different from the Kohn-Lattinger. So one way you can think of it is that Kohn-Lattinger relies on intraband screening effect, while here what I'm using is interband virtual process. Does that make sense?
okay? How would it look like in case of really large concentration of charge carriers? You have this at the end, but I somehow just didn't get. Would it really gradually go over to this conlateral if you have a large concentration of?
Right. Yeah. So if you have a large carrier density, our effective Hamiltonian, we can still analyze it, but it's not easy. Right. So in the finite doping limit, we still need to handle this interacting electron problem. But there's still a difference with Kohn-Lattinger, is that in this non-trivial problem at finite doping density, there's already attractive interaction. Right. So if you do Kohn-Lattinger, you start with a repulsive interaction U, and you rely on this intraband dynamical screening process to create an attractive interaction. But for us, the system has two bands, and we essentially integrate out the field bands. And from this process, we already generate attraction for electrons in the partial field in the active band. So that's the difference.
Okay, maybe may I continue maybe or
yeah, sure.
question. In superconductivity, especially in connection with cuprates, there was always a question whether energy gain which you gain making superconducting state is a gain in interaction energy or potential energy or gain in kinetic energy. There were some ideas by Anderson and maybe Leggett, and also some experiment by Dirk van der Marel, which claims that it might be a gain of kinetic energy. What is it in your case? Is it interaction energy gain or kinetic energy gain?
Yeah, that's a great question. Yeah, is it kinetic energy gain or is it? Yeah, I need to think about it. I don't know the answer right away. Yeah, it's a good question.
Okay, very good. Thank you.
Okay, yeah, I haven't thought in that direction, but it's an interesting question. Yeah, because of course, the full problem that we're dealing with is not just two electrons, right? So we have an entire field band, and then on top of that, that forms the insulating state, and then on top of that, I add two more electrons. So if you go back to the original problem, one can ask, when you have a small density of doped electrons, that's a regime where everything is fully analytically controlled. That what is the gain? Is it the kinetic energy gain or is it the interaction energy gain? That's a good question. I don't know. I need to think about this. Yeah, excellent question. Okay, good. All right. So okay, then let me now just to summarize what we have so far. That showing you a new mechanism for superconductivity from repulsive interactions, and here again it's really, I like to think of it as it's really just three particle mechanism, right? We're using basically two electrons plus one hole. So a total is just 3 particles. And one can understand this in real space, that there's a correlated hopping induced by by this 3-particle mechanism, and this correlated hopping is the origin of the attractive pairing interaction. Or maybe more familiar to you is the band picture, right? In the band picture, then we really have a virtual transition of electron from a complete field band to the active band, and that virtual process induces attraction. And on the technical side, our theory is really asymptotic exact at a small doping, and in particular, it's exact for just 2 doped electrons, and we do not rely on interaction expansion. So instead, it relies on small t expansion, small t over delta expansion, and it's non-perturbative interaction strength. This allows us to reach a strong coupling regime. Okay, so we are able to get a strong coupling superconductivity where delta over Tc can become very large. Okay, and and we can even get BEC BCS physics in the system with repulsion. And it does not rely on the Fermi surface, so it's different from the Kohn-Lattinger mechanism. It does not rely on any RVB physics or any spin fluctuations. We're really dealing with just a simple band insulator. And in this example, it's even spin fully polarized already, right? So it's spin does not play a role yet.
Liang,
yeah.
Does the virtual transition have to happen at the band extremum? Like in your
the virtual transition happens everywhere. It happens everywhere. So it does not happen at just near the band edge.
Okay.
So the derivation takes into account of all possible virtual process. Yeah. Okay. So let me make a very quick remark. So this limit of a fully spin polarized limit, it sounds pretty crazy, but actually in recent experiments on ABC trilayer graphene on boron nitride, and you observe the superconducting states near quarter filling, and what is called the quarter filling in this system is really most likely is believed basically to be a state of both a spin and valley polarized state. So the fact that superconductivity occurs near a spin polarized insulator, that may be an already indication that the superconducting state is also spin polarized. And if that's the case, then this model may be helpful to understand what's going on. And I also want to make some connections to magic angle graphene, the original TBG. And one interesting feature of our theory is that one important message is that when you deal with a system with a gap, right, it's very tempting to just project interaction into the active band and forget about the effect of the remote bands. But what we are saying here is that when the interaction couples the active band and remote band is not too small compared to the gap, then this procedure is actually very dangerous. The remote band has an important effect. It will renormalize the interaction within the active band. So in particular, if you look at the case of TBG, so far people realize already that if you project the Coulomb interaction directly into the active band, you already get the density interaction as well as correlated hopping. Okay, just like in this toy model that I have, and the density interaction and the correlated hopping from direct projection is comparable in magnitude. Again, that is a feature of this toy model. So therefore, it was already some speculation in the literature that maybe the fact that you have correlated hopping can lead to superconductivity. Right? So what our theory suggests that we need to actually further take into account of interband process. This virtual interband process is actually essential to obtain strong coupling superconductivity. So I think there's much more to be explored along this line in the context of TBG. Okay, now let me move on to the Spinful case. Besides moire materials, there are many examples of superconductivity in doped band insulators, right? Doped band insulators. And one of my favorite examples is this copper doped bismuth selenide. And we have early proposal that this may be a spin triplet odd parity pairing, and there has been some very interesting experiments showing evidence of a very unusual type of pneumatic spin triplet pairing. As examples, a famous example is strontium titanate, right? This is a large gap insulator, and a very small amount of doping can lead to superconducting state. So there are many others. So again, the recent experiment from Iwasa's group on the zirconium nitrogen chloride, and this compound actually has a layer structure, and the fundamental layer has a honeycomb structure, okay, formed by zirconium and nitrogen. Again, there are two sublattices in the honeycomb structure for each layer. And again, in this material, you see that the superconductivity occurs with a pretty high TC, 15 Kelvin, by doping a band insulator with a very small doping density, okay, less than 1%, right, 0.5%. And it also shows a pseudo gap and shows the BC, BCS crossover. It's all very unusual for an electronic system. And I should also mention that there's a lot of earlier DFT calculations, and it's find that it's really hard, seems not possible to explain such a high TC based on electron phonon mechanism. Okay. So so naturally, then we like to try to include the effect of the spin. Again, we can extend the model to include spins. Now, in addition to the nearest neighbor repulsion, there's also much larger on-site Hubble repulsion, right, which we call UA and UB. And I'm not going to go through the details again, but let me just say that doing the same procedure, we again find attraction for two doped electrons in the wide parameter range. Okay, this y-axis is U over V. U is the Hubble interaction, on-site interaction. V is nearest neighbor. And x-axis is V over delta. Delta is a band gap. So we see that when U is very large, right? When the Hubble U is very large, and when V is relatively small, there's this region that is non-superconducting. Okay, but in a much larger parameter range, we find two electron bound state in the F-wave spin triplet channel. Okay, so again, the low density limit is captured by a two-valley electron gas, but now with spin degrees of freedom. So there will be more kinds of interactions, both the intra-valley the intra-valley repulsion, the inter-valley density repulsion, as well as the spin exchange interaction between the two valleys. Again, we can plot the TC as a function of doping, and this calculation is asymptotically exact in the low doping limit. And we can compare this TC obtained this way. We can make a very comparison with zirconium nitrogen chloride. Okay, so the real material is obviously much more complicated, but as you can see that it has a band gap of about 2 electron volt that sets the energy scale of delta, and also the conduction band bottom is indeed centered at the K point, right? So with some effective mass, it's like 0.5 electron mass, and then we can reproduce this feature by choosing a T, the nearest neighbor hopping T, to be about 0.65 EV. And so with these parameters and use some reasonable interaction strength U and V, we find a critical superconducting transition temperature that is 15 Kelvin at 9% doping, and this value is close to the experiments. So maybe it's not too crazy. But then our proposal then is that this zirconium nitrogen chloride, that it is known to be a fully gapped superconducting state, but so far people have always been thinking along the lines of S wave, right? But what we are saying that maybe this material is actually an F wave spin triplet pairing. Okay, this F wave spin triplet pairing is also fully gapped, so it should be considered as a candidate. And the reason that we never get S wave, of course, is that because in a system with strong on-site Hubble U, for the electronic pairing mechanism, the S wave pairing is always strongly suppressed. Okay, so the final example I want to say that is an electron-doped tungsten ditelluride. This is again a monolayer insulator, and superconductivity was observed when you dope it. And here, if you can notice that the system is almost goes directly from an insulating state to a superconducting state without any intervening metallic state, right? But that's exactly in line with our theory. Our theory says that if you dope into an insulator, band insulator, you can immediately get superconductivity. And moreover, this is the experimental data of TC as a function of gate voltage, which controls the doping. And you can see the low density, TC fits very well with a square root of doping dependence. Right? So this is in agreement with theory. And finally, if it were a triplet pairing, one perhaps evidence is that when you apply an in-plane magnetic field, we can measure the critical field. It far exceeds the Pauli limit by almost a factor of 4. Even more peculiar is that at small field, we see that TC actually first increases with field before decreasing at higher field. Right. So there's an enhancement of TC by a small in-plane magnetic field. So this is totally strange and cannot be understood within the spin singlet picture. But in the case of a triplet pairing, this can have a natural explanation. So, so if we write down the free energy for a triplet superconductor, and the triplet order parameter is specified by a d vector, right? The direction of a total spin s equals 0 of the Cooper pair, and you can see that symmetry then allows basically there can be some kind of paramagnetic effect of the applied magnetic field on the triplet pairs, and this captured by this term here. And because of the existence of this effect, then TC can have a linear dependence term on the magnetic field. And this linear term will dominate in the weak field limit. And that's why we can fit the experimental data very nicely with just this, this curve. Right? So, so therefore, our proposal is that WTe2 is actually a spin triplet superconductor. So, with this, I basically finished the main part of this talk, and let me maybe quickly say a few words about the different regime, the work with Kevin, the earlier work with Kevin. So again, so far I've sort of restricted myself to the case of a model with only nearest neighbor repulsions, and one can ask, what happens if you extend longer range interactions. So when the longer range interactions is small, they can be treated perturbatively, and all this physics still remains present. But when the longer range interactions becomes comparable to the V1, comparable to the band gap, then there could be something even more interesting. Okay, even more interesting. And in particular, so with Kevin, we considered a situation. Let me start with this again, a toy model on a honeycomb lattice. With a potential difference between A and B sites. Now, in addition to the nearest neighbor of V1, let me include V2, and later we can include all interactions. And again, let me first turn off the kinetic energy T. Right? So we deal with the ultra strong coupling regime. So this is a basic classical model of charges on lattice with repulsive interaction. Now, the interesting feature.
I'm sorry. Can I shortly ask?
Sure.
If delta is really equal to 0, would your claim still remain in force?
So when delta is equal to 0?
Then delta is 0.
Yeah,
So
exactly. No. So then this method, this T over delta expansion cannot work. So so when delta is equal to 0, I think that's an interesting problem. I think that when V is large, when the nearest neighbor V is large, I think many of these features should still remain. Yeah, but the theory is only controlled at T smaller compared to delta. So the current method does not work at delta equals 0. Yeah, one needs some other methods.
It's still in the limit of T much less than delta. Okay, I see. Very good.
Yeah. So far, yeah. That's an interesting question. Yeah. Okay, so let me now talk about this different kinds of three-particle pairing, the three-particle mechanism for pairing, and that's purely based on electrostatics. So yeah, in this example, the pure electrostatic interaction, one can ask, what's the energy cost of adding 2 electrons into the system? And one can, of course, add 2 electrons on the B sites that are far apart from each other. But alternatively, one can bring the 2 B electrons nearby, and that is energetically unfavorable because of the V2, right? The 2 B electrons have now additional interaction V2. However, one can then bring 2 B electrons close to each other, and then transfer an A electron to a third B sites, right? So again, I can form this kind of a trimer configuration. So once I form this configuration, we can actually see that there's an increase of energy by delta, which is the charge transfer energy, the difference between A and B sites, on-site energy. But I've actually now gained 3 units of V2 because once I take a electron away, I saved in total 6 V2s, because previously every A electron interacts with all the 6 second neighbors, but now it's gone. On the other hand, I have to pay 3 V2s among the B electrons. I gain 6, I pay 3, so the net effect is a gain of 3 V2. Right. Now, what this means is that when the charge transfer energy delta is small compared to 3v2, is smaller than 3v2, in this pure classical model with repulsive inductions, 2 doped electrons would actually prefer to form a trimer instead of being far apart. Okay, so a trimer, the charge 2e trimer shown here, can actually cost less energy than 2 separate electrons. So we can further extend this calculation to the case of including all the interactions, and we have some phase diagram. We see that basically there's a certain parameter range where when you dope electrons will form trimers. Okay, this is the most economical way of doping charge into the system. So, and again, in this classical model, what this means is that at finite small doping density, you can have basically a Wigner crystal of trimers, and this is basically a pair density wave, right? A classical pair density wave. Each trimer has a net charge of 2e. They can form a Wigner crystal on the lattice. And yeah, so let me just skip this. Now, moreover, let's now further consider the effect of the quantum tunneling. Let's now reintroduce the kinetic energy, the hopping T's. So because of the trimer is a composite object, its bandwidth is essentially very, very small, right? Even in the presence of the electron tunneling T, the trimers have a hard time moving coherently. So it's essentially like a flat band. But once the hopping is present, the single doped electron can move coherently. They form kind of dispersive band, right? So then particularly interesting is when the dispersive band of electrons, the band bottom start to approach the energy of trimers. In this case, we can achieve some kind of resonance, right? The electrons and the trimers can resonantly interact with each other. And this problem is pretty much like the cold atom, the Feshbach resonance, right? So we have a charge E electrons, they are fermions, and then we have charge 2e trimers, which is like a molecule. And we can convert between the molecule and 2 free electrons. So this is captured by this kind of a 2-component model that is used in cold atoms. So and again, when this kind of resonance occurs at a low density, we can get a superconducting state. Okay, because of this the resonant nature of the interaction. Okay, so this is you can think of it as basically like a Feshbach superconductor. Okay, so that's pretty much all I want to say. That basically the 2 different parts of the talk. Let me just go back to the beginning. In the first part of the talk, I've described a situation where all these excitations involving charge transfer are high energy excitations, right? So we try to integrate out these high energy interband excitations. And in that process, we get some attractive interaction between the low energy electrons. So it's like a attractive interaction induced by some high energy excitations. While in the second part of this talk, I described a situation where these trimers, which involve a charge transfer, and they have a net charge of 2e, they actually become low energy excitation. And the resonant interaction between free electrons and these charged 2e molecules then can lead to a superconducting state similar to Feshbach resonance in cold atoms. Okay. So thank you. Yeah.
Thank you, Liang, for a really interesting talk. And now the session is open for questions. So any questions from the audience?
So, okay, can I ask a question?
Yeah, sure.
Go ahead.
So, hi, Liang.
Hey.
So, for this three particle pairing, what's the order parameter if I want to think of this superconductivity at the mean field level, if I can at all? I mean, whether the condensate is a two-particle condensate or it's a three-particle condensate.
Yeah, that's actually an excellent question. So I think if you if you take this model, right, that have the original model, which is on honeycomb lattice with nearest neighbor repulsion V, right, then the superconducting state basically has the pairing order parameter is between the two adjacent B sites. That can be the order parameter, but the interaction is not between the two B electrons. Interaction is only between A and B electrons, right? So there's no way you can do mean field calculation on the original model to get superconductivity. Yeah, I mean, also the original model is repulsive, right? It's a model, it's repulsive interaction. No, so yeah, so it's really all this pairing interaction is beyond the, it's beyond mean field. Yeah.
Okay, thank you.
I mean, you can describe the superconducting state in the end, maybe in some mean field description. But you will not be able to get a solution by just do the mean field calculation. Yeah, I think this also connects somehow to Daniel's question about the in the superconducting state, what is the energy gain? Yeah, that's a question I need to think about. Yeah.
Yeah. Okay. Thank you.
Any other questions?
Hey, Adrian, maybe I'll jump in.
Yeah.
Who's there?
Noah Breali.
Noah, how are you?
Thinking about cuprates. Chandravarma has this picture of kind of three bands, and
oh yeah, yeah.
That comes to mind when we think about this inter-valley singlet state. If we kind of think about that inter-valley degree of freedom as kind of like pseudo spin, right? Then it kind of this Schrieffer transformation we do, it kind of has the flavor of the TJ stuff that you do in the ordinary Hubbard. But of course, we're on the honeycomb and details are different. But I wonder if you could think about that case.
I mean, that's certainly something that we are interested in. So far, I've talked about case of the. I mean, again, the honeycomb lattice is not important. This method works for any lattice. But I've kind of purposely stayed away from the case of the cuprate for the following reason: is that in the two examples I've given, in the spinless case, at the filling of one electron, I get a simple band insulator, right? Or you can call it ionic insulator, but it's a featureless band insulator. Right, it has a unique ground state, and in the case of a spinful system, I talk about the filling of two electrons per unit cell. Again, we can get a featureless band insulator. Right now, in the case of a cuprate, the system has spin degrees of freedom, but it's also at the filling of one electron per unit cell. Right, and so the insulating state is actually a model insulator. Right, or you can call it charge transfer insulator. It's an antiferromagnetic state, so it has a spin degrees of freedom. Right, playing some role. So that makes the problem much more difficult. Yeah. So we are certainly still thinking about that, but I don't have a good answer right now. Yeah.
The other one that came to mind, you brought it up in the beginning, was the context of topological quantum computing. Spin-triplet superconductivity has a couple candidates there. The most famous one is the Ruthenites, but there's also in the background this kind of composite fermion state, the Pfaffian state, in the context of quantum Hall, right? The new Haas plateau. There's famously, I think Greiner showed it, that there's a three-body potential that has that Pfaffian ground state as its exact ground state. So that also kind of came to mind thinking about this three-body mechanism. I can send you the link if you want, but it's known in the quantum Hall community that if you put in this like kind of three-body thing and do the Haldane business, then you kind of project onto the P plus IP state.
All right. So, yeah, actually, let me also maybe clarify this a little bit. Yeah. So let me go to this picture of three particles. Yeah. So for us, the three particle involves two electrons in the active band that form the Cooper pair, and a third electron in a different band, right? In a remote band. So altogether, they form these are the 3 electrons. And in the intermediate state, right, these electrons that initially in the field band virtually transition into the active band. So in the intermediate state, we have 3 electrons in the active band, right? But at the end of the day, right, we integrate out this completely field bands. The Cooper pairing is still between 2 electrons, right? So it's a charge 2e condensate in the end. And another way of saying this is that maybe a complementary way of saying this is that we start with a model with only simple two-body repulsive induction V, right? But then the effect of the third electron in the high energy degrees of freedom is to induce a new interaction term, the correlated hopping term between the 2 electrons, 1 and 2, right? So the third electron plays a role, it comes in and then goes away. So finally you're still left with 2 electrons. Yeah.
The order parameter is like ordinary order parameter.
The ordinary order parameter is 2 electron.
It's the same for the composite fermions.
It's
so
same. Okay.
Coulomb repulsion, but you're projecting into this Landau level, lowest Landau level, and the fermions end up pairing, just a p-wave pair.
P-wave pairing. Okay, that's interesting.
But the exact, the ground state that we think is a good description, this Pfaffian ground state or the anti-Pfaffian, it turns out to be an exact ground state of the
3-body interaction. Okay.
Yeah, 3-body interaction. Yeah.
Yeah. Thank you. Yeah. Thank you for making this remark. Yeah.
Any other questions? All right. If not, let's thank Liang one more time. Thank you, Liang, for joining us today. Thank you all for being a faithful audience. And we meet again next week.
Thank you.
Have a good week. Bye-bye.